Nice. Well, thanks for setting this up and for
Yeah.
taking the time to meet. Um, I don't know if you had any vision for this. I was kind of hoping for it to be an informal, just kind of brainstorming thing because it's such a big problem.
hmm
Um, but I don't know if you had thoughts or vision on what you want it to be.
No, yeah, no, I'm super open. I have like a backup agenda in case we need it,
Oh,
but
okay.
yeah, I'm happy to go in whatever direction we want to.
Okay. Um, yeah, I don't know how do we want to kick this off? Maybe you want to start with some introductions then?
Yeah, let's do it. Sure.
Okay.
Start us off.
Say again?
You want to start us off?
Oh, sure. Yeah. So, hi, everyone. I'm Zach Stoll. I am a research engineer at New Mexico State University. I've been researching desalination for over a decade at this point, which is kind of scary to think about. It's like, oh my gosh, where did all that time go? Um, but yeah, I mean, it really started for me, at least in I think my master's program. So I went to school at Mines up in Colorado and worked with Dr. Peju and Zahi and some other great, brilliant people up there. And I really started out on the microbial fuel cell front,
Mm,
which was a really great learning experience. And I think the biggest thing I took away from that was trying to think about how to make technology more practical.
mm.
So, because that was a good, have you heard of the fuel cells before?
No, not too much.
Okay. It was a super hot topic. And Dr. Bruce Logan, I think, was one of the really big players, and he's from Penn State that I don't know if he developed it, but he had a huge hand in kind of pushing that technology and that narrative forward. But that whole space got me hooked, I think, on positive energy water treatment, or at least net neutral energy water treatment. And so I just didn't think that was possible before. And then learning from that, I worked with Dr. Jason Wren, who at the time was at UC Denver on the main campus, and then moved to Boulder, and then now he's at Princeton. So he's done really, really well. I haven't seen him in forever though, but he got me hooked on a project that one of his PhD students was working on. It was a microbial desalination cell. So taking the energy that was kind of intrinsic in the wastewater and then using the microbes to harness that energy to power a desalination process. Um, so yeah, it was just a super cool learning experience. I learned a lot. I think just thinking about problems differently than I
Mhm.
conventionally had. And so, but I followed Dr. Peishu down to New Mexico State University after that, did my PhD on that same kind of system and got a little jaded with it at the end, I think. And so I
Yeah.
was like, this thing doesn't work. Like you can't make it cost effective, kind of the surface area requirements and just battling cathode fouling and just some of these technical limitations of the system uh, kind of got me, I don't want to say frustrated, but it was beating my head up against this wall of like how do you solve these problems and then not really understanding how to do it. And so that I think took me into a pretty hard pivot into consulting engineering. And that was my big thing. It was like I want to learn how to put stuff in the ground. Um,
Mhm.
and so I learned a lot there, spent a couple years in consulting, and then got a call to work at the Brackish Groundwater National Desal facility out in Alamogordo, where I was the research scientist. And that was just a mind-blowing experience working with Randy Shaw, who was the facility manager at the time for the Bureau of Rec. But I mean, I touched so many different pilot processes out there for emerging desal tech, sat on a bunch of review committees, and so I got a really good spread or understanding of the spread of technologies that were out there that people were trying to invent and stand up to help improve desalination efficiency, performance, cost, et cetera, um, for kind of this next generation of technologies. And then got a lovely opportunity to work with NAUI. So worked with Megan Motter and Peter Fisk as the research program manager, and again, touched a whole bunch of processes out there, or didn't touch a whole bunch of, but I saw a lot of proposals and papers and got a deeper understanding of what was going on in the field. And so, yeah, and then I came back to New Mexico State to work on more pilots. And this has kind of gotten me into techno-economic analysis. I just feel like it's a really not well explored area to understand how close or far we are away from um, being cost effective and getting some of these technologies that we're piloting into commercial applications. And so that's kind of present day, but getting into brine valorization is a big one. Again, how much does it cost? Where can we save? Where are the opportunities for improvement? Um, but there's just a whole, it's such an open field, I feel like at this point where it's like you have all these chemicals and constituents or ions and salts in the water for quote unquote free essentially. What can you do with them? How can you piece those together in a strategic way where you're getting a certain product out that can be used for a beneficial use? And then how do you structure that treatment? And then how much does it cost? And who wants to own it? And who wants to operate it? All that fun stuff.
Yeah, yeah, yeah. The devil's in the details for sure with brine valorization. Yeah. Yeah, so my background, I started about 2013. So that was when I graduated from undergrad, and I worked for a membrane manufacturing company out of undergrad, and that's kind of when I was first exposed to just membrane technologies in general. The company I worked for made RO all the way through microfiltration, and it was kind of there that I was really, my eyes were open to like how ubiquitous water. I think it's one of those obvious things that you really have to see firsthand before you kind of believe it, or at least for me. And so just like how foundational water was for like basically every industry, and
Mm.
how, every process basically has a water treatment process on the side. And it was during that time there that I really kind of saw how these technologies kind of move towards certain markets. Whereas, like in my mind, like these are water treatment processes, and so they should be used for producing drinking water. And I kind of had a pretty maybe naive view on that, where I was just like, we have this great technology, but we still have so many people who don't have access to drinking water. And so after about 2 years, I wanted to go to graduate school to kind of develop my own uh, technology for water treatment. And so um, I went to UC Berkeley in environmental engineering this time, and I was connected with Bausch and Me, whose backgrounds both in membranes and nanotechnology. And it was nice that we kind of connected on membranes initially, but I think we kind of both agreed that like I could do something other than membranes, because I'd been in that world for the last 2 years. And I wanted to kind of expand my breadth. And so trying a couple different things, we eventually landed on enhanced evaporation through interfacial solar
Mm.
vapor generation, which was a lot of fun to do, but it was also kind of as like we were kind of exploring it on our own. So like she didn't have a huge background in this topic. I definitely didn't, and so I had to kind of like reach out to mechanical engineering and like other departments at UC Berkeley to like really kind of piece together the knowledge that I needed to like do research in that space. And so I was constantly confronted with kind of, internal thoughts of like someone has to have studied this stuff. Like there's got to be models out there, there's got to be, processes out there that like use this. And I think it's, some cases that was true, but in other cases it was like, oh, like sometimes we take for granted like the transport phenomenon that we're using to model, air water interfaces and things like that. So um, and so that was really fun because I just kind of got to like explore and
Yeah.
all of that where it took me. Um, I think like the target application where there was probably the most viability was for brine management, like enhancing evaporation ponds for zero liquid discharge. But I really was pushing it for that kind of that initial idea that I had, that like this technology should be first and foremost used for producing drinking water. And so, in it was kind of funny. I took my qualifying exam in February 2020, and one of the questions I was asked was like, "Oh, give us a timeline of like what you think your PhD is going to look like." And that was probably the worst time to do a timeline like that because the pandemic, like, within a month, set in. And so I was kind of able to use that to steer the project in the direction that I wanted to, but it wasn't necessarily the best fit for what the technology could do. And so we collaborated with a university in Indonesia to, see could this be adapted for use on small island communities. And we saw that there, we were able to kind of like dig into the nuance of like what contextual factors impact water access on one specific island. And what we found was that like where you lived on that island really depended on like where you got your water. And so we wanted to design for those with the most precarious water supply. And so we kind of mapped out, a map of different features that would be important. But I think my conclusion from that was that, a thermal desal process, even though it's passive, wasn't necessarily going to be able to meet the volumes for drinking water, even in that small island case. And so it was after that I did a postdoc with Many Ellen Malik, who's a pretty big name in the membrane world, and that's kind of where I was turned on to kind of two things. One, membrane-based technologies for brine concentration. So reverse osmosis, takes us up to about 70 grams per liter TDS, but then there are other membrane processes that can take us beyond that. And so he introduced me specifically more to low salt rejection reverse osmosis, where I was working with a PhD student there, Martina Del Cerro, on characterizing that technology, but also kind of into this topic of brine valorization. And that's kind of where I was connected with Naui and got to see, yeah, some of the power of techno-economic analysis to kind of guide uh, research agendas. And so now I'm currently an assistant professor at UC Davis, kind of in charge of my own research agenda and really trying to, map out the direction that our lab is going to focus on. And so that's part of the motivation for this talk is, I want to, take those first steps in the right direction as opposed to taking it towards a dead end. And so, yeah, being able to learn from you would be fantastic for me, especially at this early stage.
Oh, I think it's a two-way street here, Casey. So lots for me to learn on what you're doing too, because it sounds like you come from a totally different background. And I never knew your background before, so thanks
Yeah.
for sharing that. And it's funny how those earlier experiences can kind of shape you are, right? Obviously, as a human being, but the way you're thinking and those experiences you kind of carry with you, I'm sure very poignant ones that help shape your thinking and how you want to attack the future. So I think the more minds we have in here, it's probably going to be the better. But this will be a good first start for us to just kind of dive in.
Mm.
Um, I don't have much in way of structure on how to talk about this, except for like kind of oddball questions. So it sounds
Mm.
like maybe you have some things you'd want to tackle. So can I
Sure,
hand it
yeah.
over to you?
Yeah, definitely. I guess like the place to start is probably what we've seen the most of in this field is the barriers. And so
Mhm.
I'm curious, like, what are the most salient barriers that you've seen for brine valorization?
Barriers for brine valorization. Can we take a quick step back
Yeah,
and look at why we're even curious about brine valorization?
let's do it. Yeah, yeah,
Okay,
yeah.
okay. Because I think it's just it helps to start there to frame it a little bit. And
Mhm.
so I guess for me, in my kind of narrowish view on what I've seen here in kind of Texas, New Mexico area, is that there is, and I'm sure, California, Arizona, Nevada, this applies as well, but um, even though we kind of talk about these emerging technologies, there's still a lot of areas that haven't come around to the idea of actually doing inland desal with conventional technologies like reverse osmosis, right? And so K. Bailey Hutchinson is the largest inland desal plant, I think, definitely in the country, but maybe in the northern hemisphere. It's something big, right? North America maybe. But they're 27.5 MGD. I think they're going to expand up to 33 MGD of potable water. But you always get to this issue of like, what do you do with all the brine, right?
Mhm.
And so they're lucky where they have an accommodating formation where they can inject the brine into the ground. But I think for a lot of areas, you don't have that availability, right? You don't have that disposal option. Seawater RO is very nice in the fact that you can just kind of discharge the brine back up to the ocean. Whether or not that's good for the ecosystem or the environment is, I think, a different question. But if you are in, an area that needs a ton of water and you're on the coast, desalination becomes, I think, a lot more feasible and amenable. So, but when you look inland, where if you don't have the ocean to discharge to, you're probably not discharging your salty brine to like a freshwater body, right? Deep well injection is not very, it's not available everywhere. I'd say it's very limited, probably in the areas that you can do it. Um, what else do you have except for evaporation ponds?
Mhm.
Uh-oh, it looks like I've frozen maybe a little bit here, but I
I can hear
think
the
that's me.
audio, but yeah, I just
Okay.
see a frozen image.
Um, oh shucks, I hate technical difficulties here.
Mhm.
Uh, so, well, I'll just keep blabbering on here, but
Yeah, yeah, yeah.
if if you have to go to evaporation ponds, I think the cost of doing so is completely prohibitive. Um, and so it's just, I don't think, I think that rephrase that a little bit. The cost of disposal will prevent a desalination facility from being constructed because there's no cost effective way to do anything with the brine.
Mhm.
So when you think about conventional desalination, it runs anywhere from, especially inland in the Southwest area where there's a lot of nasties in the water, right? So you look at your feed water, there's elevated concentrations of hardness, so calcium, magnesium,
Mhm.
carbonates, and then silicates. Those are all very sparingly soluble, and the things that tend to gunk up and scale an RO process, right? Sulfates as well, calcium sulfate. Um, and so using conventional just RO with anti-scalants, your recovery is kind of pinned probably somewhere between 70 and 85%, which means you have 15 to 30% of your volume coming out as brine that doesn't have a good home for, right? And so it has to end up in an evaporation pond. And even though we're in the Southwest, or at least I'm in the Southwest here, you're on the West Coast in arid environment, the sun intensity is high, but you still need tons and tons of evaporation pond area, right?
Mhm.
And so I'd say, trying to think, the Palo Verde nuclear plant does evaporation ponds for their cooling tower blowdown. And off the top of my head, I think they generate around 3 million gallons a day of brine, and they need 200 acres.
Yeah. Wow.
So, no, I'm sorry, they need 600 acres.
Okay.
So so you need 200 acres per MGD of brine,
Mm.
right? And if you think about a community, right, that maybe needs 10 MGD of water, that means you're probably roughly generating somewhere around what, couple million gallons a day at
Mhm.
2 MGD at 80%, right?
Wow.
So that means you need 400 acres of evaporation pond. Palo Verde is outside of Phoenix, so that's a pretty hot and arid place. And so, I use a rough number that I've seen floating around kind of this consulting world of like maybe $350,000 per acre or $500,000 per acre for an evaporation pond installed. And so, I mean, that's a huge number. That's a huge capital cost. And so I think just from understanding that, you can see why people are looking and curious about high recovery RO, right? Because you get this dual benefit when you do conventional desalination. If you can shrink that brine volume, not only do you have to spend less on brine um, disposal, right, but you also get more water out at the same time. And so it's really, really nice. And I think people are moving towards that area. The question just really becomes, how do you do that? And then the next step, I think, beyond that is ZLD, right? But ZLD without brine valorization, you're just making a big old pile of salt that needs to be disposed of somewhere, right? So you have maybe less evaporation ponds. You're investing more in like thermal equipment, brine concentrators, brine crystallizers, and then you're just kind of offloading that salt to a different area. Um, and if you do the back of the napkin calculations, 10 MGD facility with 2 MGD of brine, it's like metric tons per day of salt, dry salt you would be making. And so ZLD with brine valorization, I think, is that next step of, okay, can we turn this stuff into something valuable so that not only are we not having to dispose of it, but we can generate revenue off of it at the same time and get more of a circular economy, I think, right? Because it's like, oh, if you're disposing of sodium chloride or calcium and magnesium, it's like somewhere in the world, people are mining that out of the ground, right? To
Mhm.
make some product, to ship it around the world, or to ship it overseas or within the contiguous US, if we can take that as an example. And it seems kind of nonsensical. Yeah, I fast forward 500 years, 100 years, I can't imagine that we're continuing to mine the earth the way that we do. And these processes like desalination that are you know, generating similar kind of compounds in the waste. It's like, come on, we got to be able to do something with that. And so, in terms of the barriers, I think creativity right now is the biggest barrier of like, what can we come up with to turn these salt products into that's going to be sustainable and that people are going to want.
Mhm.
Um, and so that was a long-winded answer to your question, but
No, but
what's
yeah, I think it touches on like a lot of things that I've heard in various conversations throughout the stakeholder outreach where um yeah, there's just kind of this drive, it could be to reduce wastewater volumes, it could be to increase for like to meet increasing water demand, but this drive for these high recovery processes, but just how these technologies work, the higher recovery you get, the more concentrated your brine will be, and those like sparingly soluble start to precipitate out. And so
totally?
If you are, motivated for whatever external reasons to, achieve that higher recovery, you're going to need either pre-treatment or post-treatment, and that's expensive. And so that's where like the idea first comes out, where it's like, oh, like why don't we try and make money off of this process as opposed to just thinking about it as a treatment process? But then that becomes trickier because it's like, okay, we can, even if we have the technologies to isolate these constituents, then someone has to buy it. And I think that's like the other barrier that I've seen a lot of times is that there's not really a purchaser that meets, a very specific set of criteria in order to kind of offtake those constituents. And so, yeah, I think like those are the kind of the dual things where it's like valorization is like crucially two steps. It's
Mhm.
isolation and it's selling. And we're like still working on the step one, but step two also we can't neglect that. Because then yeah, we run the risk of producing a high quality product that no one's going to buy.
Yeah, and I think there's some examples on the East Coast in the Marcellus Shale of a company called Eureka that at the time had a ZLD facility for produced water treatment up there. Um, and I think their off-taker bailed on them. And so they just kind of stockpiled all of this salt on site and on site. And it's just like, oh my God, how do we get rid of this? And it
Mhm.
becomes such a liability. And so, yeah, to your point of like, we need to be able to sell that into a market. And all the nuances that come with that are going to be challenging but fun, I think.
Yeah,
You just sort of the first one that comes to mind, kind of, to your question of like, what are these barriers for brine valorization? Purity, I think, has got to be up there,
yeah,
right? Um, if you want to compete selling calcium carbonate, or if you want to make a hydroxide, right, calcium hydroxide, or even acid and base, right, from bipolar ED, which we can get into. Um, what are your purity requirements? I think if you're competing, trying to compete in that same market, it's going to have to be really high, right? Because if you get super high grade calcium carbonate, that's used in like paint, that's obviously used in cement manufacturing, but the purity can be different there. But all these different end users have certain purity requirements because they've done all the work to understand the amount of impurities that they can withstand, in their process for it to be, um, yeah, marketable and effective.
yeah, yeah. And I think a common critique that I hear with kind of this like this purity trade-off, uh, which like I think holds more water in an abstract sense, kind of where
Mm,
researchers tend to operate, where it's like the higher the purity, more cost associated with it, but also the smaller the market likely is for like taking that commodity. But I think on the flip side, in the real world, like we really need to also space these things like geographically. And so, it may not matter, how large or small a certain market is. It's like what is local because transportation also has a cost. And if they need a high purity product, then like that match could be enough for that, that case, and then we can build from there is kind of some of the thinking that I've had on that.
Oh, interesting. Yeah, and I think another way to attack that problem is like, can you find markets where high purity isn't a requirement?
Yeah,
And
yeah,
so, for the guys at Blue Brine, it's the brine valorization facility that's attached to K Bailey. Um, they are, I think, selling some of their product into an industry where they don't care as much about the purity too much. So acids and bases, that they have off takers for, I think they just need the protons and the hydroxyls, and they
gotcha.
don't necessarily care how much other stuff comes with it. I think to an extent, I'd
Mhm.
love to learn more about that. But yeah, I mean, maybe there's these niche applications where it's like, yeah, we don't care if it's super duper pure. Like, we just kind of want it cheap, and if he has some impurities in it that we can deal with, like we'd be happy to get it for half price or 25% off or something like that. So,
Yeah, I think one thing that we've encountered with trying to connect like the calcium and brine with cement manufacturers is kind of the
mm,
opposite problem where it's like we're able to the only way we can kind of isolate the calcium carbonate is like through a process that gets it pretty pure. It's like
right,
pretty I want to say like 95% purity, which would probably be low for like food grade applications or pharmaceutical applications, but it's way high for cement where you know their original source of limestone is just like from quarries. And so
right.
and so like the cost of kind of achieving that higher purity, which is just a function of like how efficient that chemical precipitation process is, doesn't have added value for that particular off-taker of a cement manufacturer.
Oh, that's interesting. So is that just a benefit for them? Like if you had this treatment train that was producing the calcium carbonate as kind of a byproduct, right? And they were a viable off taker, is that just an added benefit for them to be accepting a higher purity product for maybe less money? Or are we over treating it?
I think it's over treating it. Yeah. So
Okay.
I like they don't really care about the purity because limestone has a lot of other things in it, a lot of other
Right.
minerals that their process can withstand. Um, and so yeah, like it's like over treatment. I think is like a manner of perspective. Like on the cement side, they would probably view it as an over treatment. On the water treatment side, they're just trying to use it like remove it for pre-treatment essentially. And so
Right.
and like just the product that forms is one that is just kind of this kind of middle ground purity that we can't really find a good market for yet.
Yeah, yeah. There's a lot of different things to balance there. I'm totally with you on, concrete and cement manufacturing because it's just such a wide, fat part of the line where you could dump a lot of calcium carbonate, right? Because the calcium carbonate mass that we would get out of, I feel like the collective desalination um, systems in the United States, including seawater desal, like,
Sorry, someone ring the doorbell. That sets my dog.
oh,
So
oh,
so you shut him down.
oh, it's cute. Um, No, sorry, no, that's cute. Always in favor of a pet break if we need one. Um, Mine's probably outside the door crying right now.
Here, let
But
me take care of him real quick
yeah,
and
yeah.
okay, sorry, one sec.
No, you're good.
Let's see, cause so much ruckus. I'll
Oh, hi,
take
buddy.
a little uh, cameo for
That's
the
cute.
call. Yeah, little guy, but he makes a lot of noise sometimes.
Oh.
Yeah.
Where was I? Where was I going with this? I guess I was curious about, because we have the ability, if we have the ability to push all of this calcium into cement manufacturing, I think theoretically they could take it, especially if it was of, sufficient purity, just because
Yeah.
how much we would generate from all of the kind of collective desalination processes inland and seawater. I don't think it would make a dent in how much cement is manufactured in the United States, like as a whole. I'm sure there'd be like local regions where it might be like, a couple percent higher than other areas or like the average, but my back of the napkin showed, I think it was less than 1% of the total mass. Like if you accounted for all of the calcium that you could precipitate out as calcium carbonate in a pretreatment process for desal, like they just do hundreds of million, what do they do? Millions of metric tons per year, and
Yeah.
we'd be so, so low.
Yeah.
But but I think my subsequent thought on that is, okay, it seems like a valuable and viable place to try to stuff this waste, but
Mhm.
we are still sort of contributing to the CO2 emission issue,
Right.
right? Because it's like what 8 to 10% of global CO2 emissions come from kind of cement and concrete manufacturing as a whole globally. And so if we're adding calcium carbonate into that, is that good? Are we making the problem worse? How do you think about that?
Yeah, yeah, yeah. No, I wanted to circle back to kind of like that, like the balancing of supply and demand. Because yeah, that's one thing that we tried to do was run a mass balance to see, like are we like 1% of like the total demand? Are we
Yeah.
10,000%? Because that's also a problem,
Yes.
and one of our team members, Caroline Atkins, actually did a really good job of kind of doing this mass balance by state. And I think
Oh.
there's a lot of mismatch. I think like in some of the states, California actually had one where like it was like a double digits percentage of the total amount. So like it seemed like there was some opportunity there. But yeah, like I think with any industry, it's like, yeah, you really have to balance the supply and the demand. And yeah, with regards to the the carbon intensity of cement manufacturing, I agree. I think like we have to think about what is the source of the carbonates, and like oftentimes in groundwater, it's coming from these geological formations. So it's like already CO2 that was in the ground that is coming back up. If the CO2 was coming from, say, carbon capture or something like that, then it's like slightly less of a, carbon intensive step. But there's carbon embedded in processing and transporting these materials around, but at least like we're not releasing additional CO2 to the environment. And so yeah, I think that like that's another barrier, especially with this particular commodity that we've run into, is that calcium carbonate, in this, decently pure form doesn't produce enough advantages for the cement industry to kind of change how they configure their supply chains to accommodate this new source. And so if we were to, produce something like calcium hydroxide, I think that there's potentially more value there. But at the same time, that CO2 is needing to be removed from the water at some point. And so, it's
Mm.
just a matter of where that CO2 ends up. And is it just that we're releasing it ahead of supplying it to the cement industry versus within the cement industry?
Yeah, yeah. So getting back to your one of your original questions about where are the barriers, I still
Mhm.
stick with my answer on creativity because it's like there's
Yeah.
got to be something. And so I love the fact that you guys and you and your team are looking at conventional outlets for it. And so, but I just always wonder if there needs to be an entirely different market developed and created
Mhm.
for the brine valorization stuff. Um,
Mhm.
or if it's a blend, but can you do
Yeah.
batteries in some way with some of the calcium? Um, can you, I think we had talked about it via email. It's like, can you make a bespoke concrete of some sort? And I'm just walking it. We have new
Yeah.
cats, and so they broke a lamp the other day, and I was just like cleaning up the pieces, like, huh, like could you make a like lamps and like house furniture out of some of this as well? Like, would you make a new cement or concrete company that
Mhm.
made pretty much bespoke house products, right? And my mind just jumps to, oh, usually consumer products have higher margin. You wouldn't need to produce as much. I don't know if you'd be like, would you be held to the same standards? Because it's not necessarily structural, right? If it's more of like decorative or hobbyist cement or something like that, could you get away with that? Um, Pavers might get you into a different area where it's more difficult, but I was trying to think through the process a little bit more of like, okay, what else would go into this? And I think, the heating component of it as well, right? So you mine the limestone and then you blow off the CO2 when you heat it, right? But then you're also using fossil fuels at the same time to do the heating. And so I think that's where the other kind of half of the CO2 emission story comes from when you're talking about cement. And so, but there's a really cool company that is using a solar thermal um, new type of technology. The company's called Synhelion, and they have a project with Sandia National Labs right now where they're trying to use only renewable energy, right? All the incident sun, focusing
Mhm.
it on a certain point to hit kind of that 1500 degrees C temperature and then bake the limestone to achieve the same results. And so, but I wonder if that coupled with this project we're working on with Bureau of Rec of the calcium hydroxide based kind of cement, um,
Mhm.
net zero, right? Would that be theoretically net zero at that point in time? Um, and what, yeah, I don't know. I'm rambling on here, but it just seems like the landscape is changing, and there's so many degrees of freedom that you could take advantage of, to either start a company or to at least allow us to think about things differently than we have been conventionally.
Yeah, yeah, yeah. No, I like your framing of it, because this kind of, what sparked this conversation was kind of a comment that you made where it's like, yeah, are we thinking about this incorrectly? Are we focused too much on supplementing existing industrial ecosystems as opposed to replacing
Creating
them
a new one.
for
Yeah.
sustainable? And so, and yeah, like I don't see why, you know, brine is different from any other kind of wastewater or even like solid waste stream, where it's like, if we have an abundance of this, can we find, can we turn it into something useful? And no, yeah, like that's useful, that's safe. I think like that was like one of the comments from the initial stakeholder workshop that we had, was that like, what is in groundwater? You have calcium, magnesium, chloride, silica, um, but then you also have like trace levels of pretty much everything on the periodic table. And so, and like a lot of that includes radioactive, like naturally occurring radioactive elements. And so it's like, if you're precipitating something out, just be careful that you're not concentrating those things. And so I think like, yeah, there is like a safety element to it, but like, yeah, I think that like what if we were able to kind of take this existing process that works well, that produces drinking water from groundwater, and then on the tail end of that, like turn it into like an all sorts of, like yeah, like you said, like a kind of a local like raw materials manufacturer. I think that could like spark a lot of different things where it's like, yeah, I think oftentimes we think about markets forming around demand, but like a lot of times it forms around supply. Like it's like you just have a lot of, like plastics, for like it was a byproduct of oil refineries. And so now we have plastics and everything, to the, benefit and detriment of our society. But yeah, like it was like not necessarily like people wanted this thing that they didn't know that existed. It was they just had an abundance of this thing that was dirt cheap, and then they can make a whole industry out of it. And so yeah, I think like similar things need to happen around a lot of different waste streams, including brine from these desalination processes.
That's super interesting. I guess I had never thought to think of the oil industry and how they turned a lot of their products around because they make so much stuff out of a very similar, the same source of
Mhm.
materials.
Yeah.
So
Yeah, I was trying to think of like successful examples of like waste valorization, and I was like, oh, there's just not that many out there. But I was thinking more about, I'm like, well, maybe that's not necessarily true. Like another one is like fly ash from coal, from like
yes,
burning coal, and then that for a long time that was just like a solid waste that would be landfilled. And now it's being used by the cement industry as a like supplemental cementous material because it has this calcium and silica content that can help offset the amount of calcium carbonate that they need. And so it's, taking the outputs of a pretty, pollutive industry, but it makes, another industry that has a very carbon intensive process more sustainable. And so it's just kind of interesting to see these trade-offs. But like that is an example of waste valorization.
yeah, totally. I think sticking with the power industry, didn't a lot of calcium sulfate and gypsum reuse come out of the power industry? I
So I
think
think,
EPRI helped kind
uh-huh.
of do a lot of the preliminary research and get that up and running because calcium sulfate is a big kind of byproduct from cooling tower blowdown and flue gas desulfurization wastewater treatment. And so I
Mhm.
think they came up with a similar approach of like, oh my gosh, we've got all this waste. How do we get rid of it? It's like, oh, it's pretty pure. Can we just stuff it in wallboard? Like some sort of construction material, right? And so, yeah, and then I think even in the wastewater realm, aren't people doing struvite precipitation um, from anaerobic digester concentrate to make fertilizer? I thought there were companies out there that were executing on
So,
that.
yeah, I believe so.
It's,
Yeah. And so yeah, there are like these. Yeah, I think so. It's like that's kind of like the part one of valorization. I think we are getting better at where it's like
yeah,
we're able to isolate these things, but now it's just kind of matching those with the appropriate market or developing a new market for it. And
yeah. Yeah, you got me thinking now, Casey. So it's probably a dangerous thing. Um, I was harkening back. What was that? I had a trip. I went to water reuse last week, and I had some, downtime to think about some of the brine valorization stuff. And I was remembering a comment you had made about potentially using it as batteries or something. I thought you had made that comment at one point.
yes, yeah, or like I think like thermal energy storage.
Yeah, yeah. Have you had more thoughts on that? Because I had originally dabbled in this, I don't know, many years ago, and I was just like, oh, I wrote it off, like, oh, that won't work or whatever, like that. But I was rethinking it again. Um, I don't know. I'm curious. I think
Mhm,
I shouldn't write it off. I think I should probably do a much deeper dive on this, but the setup is really interesting in that, like, if you imagine you have a desal plant, you would just constantly producing this compound,
mhm,
right? And that seems obvious, but it's like, what if you were making batteries like consistently, right? And what
mhm.
if you were operating for 20 years? It's like maybe you made a battery every day or every week, and then
Yeah,
it just contributed to more and more storage, energy storage, and you just continued to build into that over time. And maybe that becomes a regional thing. Like it's dirt cheap, maybe it's not the most effective, but if you could make it work, you're just always getting more energy storage.
yeah.
It just seems a nice way to leverage kind of a regional problem that you might
Mhm.
have.
Yeah, yeah, yeah. No, like I haven't thought too much more beyond what we were talking about before. Um, but yeah, I think that was one of the, my backup, points that we could talk about is like the thermal value of brine, where like it can
Yeah.
store
Ooh.
energy, but it could also like as we are like say evaporating it off, that's an extreme cold sink that we could utilize. And so cooling is a huge hot topic for data centers and all sorts of other things.
Yeah.
And so if what if in part of the like concentrating process, we like implemented this kind of this cooling step where it just provided like a heat sink for what a neighboring process. And so and then then you have a more concentrated brine that could be used for thermal energy storage. So like I could see like it going both ways.
That's interesting. Too many things I need to do deep dives on.
I know that's the fun, but yeah, like overwhelming element of brine valorization where it's just like, yeah, like as you dig deeper and deeper, like yeah, like we said at the top of this, like the devil's in the details, but that's also where the exciting research questions are. And so yeah, it's been fun talking to all these folks, but I feel like I have way more questions than when I started this project than answers. And so yeah, I guess that's kind of why we're in this line of work is we really enjoy searching for answers to those questions and are okay with the fact that it may lead to just more questions. And so
Yeah, yeah. I think I get more and more excited about the new questions that it poses the
mhm.
longer I'm in the field. Because it just feels like that's never going away. I feel like I'm never going to get to the point where like this is the answer to the thing I've been looking for. It's always like another whole subset of questions
Right.
that need to be in. Like it's very fractal, right? And it just keeps going and going. And yeah,
Yes, yeah. So
job
uh,
security.
yeah, no, that is true. And like hopefully, yeah, like I think like it's such a like we were talking about earlier, like this doesn't just apply for Brine. Like it applies to all sorts of things that could, be the tipping point towards, achieving that vision of a more circular economy. And I think, yeah, like, but yeah, there, yeah, all sorts of implications of like, which industries are sustainable, which aren't, which are, foundational to our society, which aren't, and like, so I think that like, yeah, this is a very multidimensional problem that goes beyond just kind of how we view problem solutions as engineers.
Yeah, yeah. Um, I know. I was at Reuse, now we had a poster up and Peter and Megan were there to talk about kind of how they were thinking about Maui 2.0. And I always found the regional aspect of some of the upcoming foe is extremely interesting. Um, Megan's brilliant, and I know she's probably 10 steps ahead of everybody thinking through this, but what I haven't started to think about it, but you're making me think about it now a little bit more deeply of, does brine valorization have much more of a regional and local impact than just water treatment? Because I think water treatment's very narrow. I don't know if that's the right word, but it's like you don't have water, you don't have drinking water, so you make a desalination treatment facility, right, to give you more water. Right? Very general example. And that's about it. Because it's just like, oh, you're going to fold it into the existing distribution system and you're going to give it to your customers. And that's kind of the thought process there. But when you start thinking about brine valorization, it's all these other things on top of it that have to be considered of like, what am I going to do with the brine? If I'm going to valorize it, like who are my off takers and does my chemistry in the water like
Mhm.
sufficient to satisfy all those different demands and metrics that you'd have to kind of go down that checklist of. And so it just seems like it's much more of a regional problem than it is like a water treatment problem.
Yeah.
So have you thought about that at all?
Yeah. I think so. Like, I think like it was an idea that like I think was starting to germinate when we were talking last was kind of like maybe the supplemental approach, like the pathway for that is like, okay, like where am I located? What industries, like large industries, are nearby?
Oh,
And then what is their supply constrained commodity? And can I produce that from this brine? Is it acids and bases? Is it calcium? Is it silica? Um, and then how do I achieve kind of the purity specs that they need for their process? And then I think then it's just like that framework is the scalable part about this, but where valorization in other places like gonna look totally different. The process that they use, the industry that they connect with, the purity specs that they require. Like it that is like the harder part to scale, but I don't think that maybe that's not the goal. I think the goal is to like really like try to make these brackish groundwater desalination plants more resilient by connecting them with other resilient or robust industries.
oh. That's interesting. So sorry, Casey, remind me, is part of the project that you're working on right now to develop this framework of like how do you think through as like a desalination plant? Like what perspective are we supposed to be imagining ourselves in
Mhm.
walking through your product project? If you're are you first off, are you making this framework of trying to how to like think through the valorization stuff?
I am like working on, yeah, some semblance of a framework, but like we're
Okay.
mostly trying to explore a few different commodities. And so we've kind of taken this, it's like the abundance approach for valorization, where it's like we're focusing on what's there as opposed to
Okay.
like the high value, like high abundance versus high value. And so the high value would be like, oh, like are there critical minerals that we can try and extract? And but usually the concentrations are so low, and the technology is not there to separate them out from everything else that is there. And so I think early on we kind of made a decision that we're going to focus more on the higher abundance. And so from that, there's calcium, there's sodium chloride, um, there's like gypsum and things like that. But I think like the two main things are like the calcium and the sodium chloride that we focused on, and like
Yeah.
what markets do those fit into. And so my job is kind of more to kind of figure out like, do these products fit in these markets? And if so, like what would their purity specs be? Because that would inform the other side of the project, which is kind of doing techno-economic analysis on the valorization trains that would be needed for that.
Right, right. Yeah. Oh man, so many different components.
Yeah.
Think it's cool to hear that you're focusing on calcium and sodium chloride. I think that's where the TEA has sort of directed me. I still get hung up on the calcium,
Mhm.
um, for all the reasons we talked about earlier. But where are you seeing sodium chloride value?
So I think initially, like we were exploring just kind of like we were taking a similar approach to calcium, where it's like, okay, like when people say calcium, people think cement. And like for sodium chloride, I think people you could associate that with like say road salts. And so we haven't been able to dig too deep. We're trying to contact like different departments of transportation and things like that to like talk to folks who are in charge of like procurement of salts for road weatherization. Um, and so I think like two, that's like one side of it too. Like road salting is also not the most like sustainable practice from like a water
Mhm.
treatment standpoint. And so there's kind of some like challenges like, oh, if we're trying to tie brackish groundwater desalination plants to kind of other sustainable industries, is road salts one of those? Um, and then I think like from our conversation, like the ability to produce chemicals from sodium chloride, I think is a like a big opportunity, but I think we haven't really thought about it from bipolar membranes, but like kind of from other like like more traditional unit operations. And even then, it seems like there could be value if there is a purchaser for it. But
Right,
if you're able to shrink all that into a single unit operation, that make it all the more financially viable. So I think like, yeah, like to your point, like the production of acid bases or acids and bases with um, like the sodium chloride, I think has like a lot of value and a lot of flexibility because like most industries need acids or bases, even water treatment need acids and bases for their process.
right. Yeah, yeah. It is such a lovely opportunity. Um, the bipolar electrodialysis at the end. The challenge is just all that upfront work that you
Mhm.
have to do in order to get it to a certain purity, right? If that's what you need.
Yeah.
Um, and as we dive deeper in our Nowie project on this, though it seems so dumb in retrospect that it took me so long or took us so long to think of this, but we were realizing that we're getting a lot of quote unquote contamination from potassium.
Mm.
And so we've done a lot of work to separate monovalence from divalence, right? Using selective electrodialysis, or electrodialysis metathesis, which are kind of two different flavors of ED, that really leverage some of the newer membranes that are being commercially produced right now. So you have this option to kind of get calcium and magnesium in one stream, right, with sodium in another stream, um, which is really nice. But we don't have a good way to get potassium removed from sodium. And so
Mm.
as we kind of follow the ions in the treatment train, we'd really only been focused on calcium chloride, magnesium, silica, I mean, we do the full spread of it, but when we were kind of doing our mass balance through the system, we somehow dropped potassium and like nitrate and ammonia. And so we
Okay.
really need to go back and revisit those. But potassium's at a relatively high concentration for us on the influent. I'd
Interesting.
say probably a few hundred milligram per liter, a couple hundred. And so by the time you concentrate it up, it just like it follows the sodium and you end up with thousands of milligrams per liter going into a bipolar system. And so you'll make HCl on one end, right?
Mhm.
But then you're also going to make NaOH and then KOH. And
Right. Yeah.
so the question is, is that purity okay? Like, are you just looking for the hydroxides? Because if not, like, I have no idea how to separate sodium from potassium. I think
Right.
there's some solubility differences, but the concentrations they're present at, I think, would pose a challenge because
Mhm.
sodium chloride solubility is like 350 gram per liter. I think potassium is closer to like 200 to 40 gram per
Yeah.
liter, but it's just present at such a lower concentration. If you concentrate them up at the same time, they're both probably reaching saturation at the same
Right.
time. And
I
so
see.
it's like, there's no way to really arb that. And so, yeah, it's a big challenge. I was all hot and heavy with bipolar. It's like, it's going to save the world. You
Uh,
get that when you first, looking at a technology and it's all sexy, it's cool, it's very
mhm.
promising, right? And you have those rose-colored glasses on and you're in the honeymoon phase. But yeah, as that honeymoon phase starts to disappear and you do the devil in the details, start looking for
Uh,
those, you get all these little nuanced challenges coming up that are like, oh crap, how
mhm.
do I deal with this?
Yeah. Yeah. No, that's such an interesting challenge. Yeah, I think like especially, I mean, we hear a lot about this with lithium because it's like also monovalent, very similar in size to like say magnesium, but they have a different charge. And so like
Right.
there are all these that you have charge and you have size, and then like beyond that, there's like not a whole lot different. I guess reactivity would be the other.
Solubility, yeah, reactivity.
Um, and so like so then it becomes like very, very challenging, especially for these monovalents to separate them from one another in a cost-effective manner. Like I
Yeah.
think that's the other thing. It's just like you could do it, but it would take like infinite space and infinite money to like actually, yeah, like to do it at scale. Uh, and so yeah, I think one direction I'm interested in potentially in like taking my lab is really leveraging differences in phase. And so
Mm,
like we are kind of and who knows, I have to do more digging into this, but like we're kind of used to the properties of certain constituents in like an aqueous stream at like normal temperature, pressure, and conditions like that. And um, but like when you change those conditions, like the temperature or the pressure, your system like the properties change in response to that in different ways. And then I think like things that like behave very similarly start to behave differently. Um,
right.
and so, but yeah, like changing your temperature and pressure is a very energy intensive thing to do. So I don't know if the cost really works out, but I feel like that there is a lot of potential in like yeah, like if we were to like rather than kind of focusing on just these kind of aqueous separations in an aqueous system, like are we if we were working with a supercritical system, does that change how we can separate these ions out?
I've got to plug you into some researchers over here at Los Alamos National Lab.
Hmm.
So Dr. Prashant Sharan
Okay.
is a contact that I have over there, and he works specifically on supercritical water desalination and
Okay.
oxidation. And so theirs is cool. Theirs is more focused on produced water,
Hmm.
kind of raw produced water, I guess, where there's quite a lot of organics in there still. But they
Hmm.
go to the supercritical phase for water, right? High temperature, high pressure. And when you have this soupy mix in the produced water of like lots of organics and then high salts, what they're finding is the oxidation, like you have to kickstart it, right? You have to use some energy to get this thing off the ground. But once it kind of gets to a steady state, it oxidizes the organics in the water in situ and uses that to help drive the process. So you're kind
Interesting.
of doing like little mini explosions. I guess I'm
Yeah. Yeah.
envisioning. He's probably going to kill me for getting this all wrong, but there's something that's happening where you're generating a lot of energy, right, within the reactor system, right? You're breaking those fuels down, um, and they're finding that they also can precipitate out different compounds at different parts of the supercritical cycle. And so as they're ramping up the temperature and pressure, certain things are falling out first. And so, to your point about the supercritical phase and looking at different phases, like there's got to be different opportunities there. And so if there's sufficient organics present, I think it's cost effective. I don't know what the exact numbers are, but you don't have to use like you have to kickstart it, right? But then the energy within the process can help drive it to a certain extent. And then you can capture some of the waste heat, right? Recycle that. They're also looking at coupling that with some supercritical CO2. And I honestly forget what the application is. Some of this stuff is just
Yeah,
so
yeah, yeah.
way far out of my brain, but yeah, there's got to be different ways to do this stuff. And so if you're interested, would love to plug you in, connect you with him because I'm sure you guys would nerd out.
Yeah, no, that'd be amazing. That'd be incredible.
So yeah, they've got a pilot one that they built for a big DOE project. I think it's up in Wyoming right now,
Okay.
but that's kind of the phase that they're at. They've done it on the bench scale and they've built a much larger one and are doing field validation. So um, I don't know where it fits in aside from produced water. Maybe some of the semiconductor wastewater, because I
Yeah.
know they use a lot of solvents there. I think
Right.
some of the
Mhm.
plants and the fabs are better at segregating like some of the high, nasty recalcitrant streams into one bin, and then you have other kind of aqueous streams going into another. But I also know that some of them do not do that. And I think that
Yeah.
was a big issue here in New Mexico is we had some interest in some of those manufacturing companies, but they kind of coalesced all their waste. And so to build a ZLD facility around that was like extremely challenging because of the recalcitrant organics. So but then
Interesting.
also DPR brine. Like I feel like nobody's really been there yet. So would love
Yeah.
to hear your thoughts on that. But as more communities go to direct potable reuse, right, you're gonna get more of that fresh water out of the wastewater, but then your brine isn't the brine that we typically think of from like a typical desalination facility, right? This is
Yeah.
going to be organic laden,
Mhm.
possibly viruses, bacteria, other things that are in there.
Mhm.
Um, how do you treat that?
Right.
Especially
Yeah.
as right because it's like those reuse facilities are only becoming more prevalent, and
Mhm.
so that just means your waste volume is going to go up. And
Mhm.
how do you tackle that?
Right. Yeah. 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 That was actually one of the topics I got to dig into during my postdoc was like municipal wastewater reuse concentrate. So like, a big mouthful, but yeah, like it's like as reuse becomes more and more prevalent, we're gonna have this unique wastewater stream that's also gonna be more and more prevalent. And I think yeah, there's wastewater is kind of managed differently than like drinking water. And so like a lot of the literature is like there's like kind of this like gravitational pull towards like, okay, like treatment for the drinking water side, but like not as much for like what do you do with this concentrated brine. And so I think like yeah, that oftentimes gets externalized into how we just manage wastewater in general. It limits the different environmental outlets because it is more concentrated. uh, but yeah, it's definitely like I think a big challenge where it's like you have these uh, contaminants that like everything that like you didn't want in there for human safety concerns is like in this brine concentrated brine stream. And then you also have other things that are like hazardous to the environment too, so like things like copper and nickel that like might be in trace amounts but that can really have a devastating impact on like say a fish population if it were to be discharged in that manner. Um, and so yeah, so I think like it's a lot of the like how that's currently being managed is similar to how we manage brine in a lot of cases where it's like but it's like in municipal it's like in like urban centers as opposed
Right.
to maybe being like you know by a power plant or like just like outside of kind of city bounds. And so I think a lot of times right now it's the volumes are small enough that it can be usually it's managed by discharging into the sewer network of a larger municipality that can like basically
Mhm.
dilute that. But if they do reuse, then it's like it's just kind of like kicking the can down the road until I think that like I was having a conversation with Megan Plumley. It's like, oh, like are these systems like just daisy chained together until eventually one is outlets to the ocean and that's where the brine eventually goes? Is that the approach that we're looking at right now if we don't like plan accordingly?
So what's the answer? Does it all just go to the ocean eventually then?
That's kind of, I mean, that's kind of like the current framework right now. I think like
Okay.
because like ZLD technologies is just like too expensive. I think like there's opportunity if like we were able to lower those costs and like maybe like reduce their spatial footprint. Um, then like there's opportunities to like maybe like concentrate that brine and then like pipe it to a ZLD center or something like that where it can be managed and then maybe even valorized. But yeah, like that piping infrastructure can be very expensive if it's not there. already.
Yeah.
There's like only a few instances where there's like, dedicated, or there's probably a lot of more instances beyond what I know, but like I know there's like one kind of more well-known one in Southern California, the Inland Empire Brine line, that basically brings all this desal brine from industry, from drinking water plants, all the way to basically Orange County Water or Sanitation District, and then they treat it with their system, and then it gets discharged to the ocean. But if instead of going there, or maybe at the outlet of that before it goes into the system, like if there was like a treatment process there instead of kind of blending it and sending it to the ocean, you could like create that as like a barrier to the environment.
Yeah, that would be nice. Because it's just there seems to be so much talk and discussion around emerging contaminants, right? But
Yeah.
at least from where I sit, and I'm not super deep into that field, it just seems very, I think, focused on drinking water health. But all these things are in wastewater, right? Um, and so yeah, if you're doing DPR and that's getting discharged somewhere, you're just kind of concentrating it up and moving the problem somewhere else.
Yeah, yeah.
Yeah.
No, that's so true. I had a fun conversation with a old colleague of mine. Her PhD was on PFAS research, uh,
Okay.
and so like we were just like I just like whenever I have a PFAS question, I like call Emily Cook up and like get her opinion on it. And we came up with this like analogy for PFAS, where it's just like if there's this Dr. Seuss book. I forget. I should look up the name of the book, but it's called like, or it's on like the pink ink, I think is what it is. And so it's like this like
Okay.
kind of it's like these kids and they like there's this like kind of like pink goo that appears and then they like keep trying to like spread it out so that it doesn't like it doesn't look as bad, but it just like kind of gets like bigger and bigger and bigger. And like um I feel like PFAS is kind of that way where it's just like, okay, we can put it over here or over there, and like
Right.
it out of our drinking water is a good thing, but it's still like in these ion exchange resins, or like it's in your brine, so then you also have to like deal with it over here eventually. But like right now that's like not the primary focus, which like I totally get from a human health standpoint.
Yeah. Tons of different challenges. And I'm
Mhm.
sure we could go on for hours on this,
Yeah,
but I do want to be respectful of your time. I know we're kind of at the hour. Should we wrap up and maybe have to have a round two of some point?
yeah, no, that sounds great to me. Yeah.
Well, cool, Casey. Man, I can't believe it's already been an hour. This has been
I know.
fun.
Yeah, yeah.
I feel like I don't get to nerd out on a daily basis like this anymore. Just because I feel like I'm getting so specialized in my field. It's tough
Yeah.
to come across, I think, different experts who've thought about it as deeply as you have. So
Yeah.
I really
No,
appreciate it.
no, I same here. Yeah, I think like especially in this, like as you become more specialized, yeah, you become more isolated in a sense, and like and just like fewer people that you can like really talk deeply about these like thoughts and concerns and curiosities that you have. And so it's like I'm glad that like our fields are close enough together that we can
Yeah.
use each other for that purpose.
Yeah. And we'll have to get you out to New Mexico sometime, and I'll have to, I think, probably invite myself over to your lab at
No,
some point
please.
in time next time we're out
Yeah,
in California. So
that sounds great. Yeah, once it's we're still setting everything up, but once it's up and running, would love to have you.
great. Well, thanks so much, Casey.
Yeah.
Um, yeah, maybe we could wrap it there. Would you be able to send the recording over when you get a chance?